My name is Mario Martinez, and I come to you from the School of Education at the University of Redlands. Today, I am going to be talking to you about what I call the science of higher education, which is the title of my latest book. Here is a brief quiz to kick us off. If you get the correct answer to the quiz, please email me to schedule a 20-minute Science of Higher Education conversational follow-up. What do the 4 items have to do with each other? The answer: all of them are explainable by a math equation known as the power law. We won't go into a lot of technical detail, but a power law may look like either of the shapes that you see on the screen now. Many of us became familiar with graphs that look like the left side of your screen starting in 2020, when Dr. Anthony Fauci and others explained the rapid spread of COVID, or what we might term the exponential spread. A power law models this spread quite accurately, as it turns out. Health officials told us to try to flatten the curve through social distancing and mask wearing. When it comes to modeling the weight and appetite of a cat versus a mouse, the difference in road miles between 2 cities, or the public funding a state like Florida provides to public higher education versus West Virginia, the graphs look more like the right side of your screen. For example, Florida is 11 times bigger than West Virginia in terms of population, but provides less than 11 times the public funding, a pattern that generally holds when comparing states of different sizes. Or New York City is about 4 times bigger than Houston, but its infrastructure needs, like road miles, is less than 4 times, a pattern that generally holds when comparing cities of different sizes. In this video, I am going to emphasize power law or scale relationships in higher education. We will cover the 3 objectives you see on the screen, and you can pause the video to review them if you need to. Let's start with the first objective, by digging into that cat and mouse example. This graphic models several animals, including the most vicious of all, a man, by how much they weigh and how much they eat per day, also measured by what is known as the metabolic rate. If we had a piece of paper large enough to graph animals as small as a mouse to as big as a whale, it would look like the little left-hand curve we just saw a few moments ago and shown on the left side of the graphic now. But there is not a big enough piece of paper, so mathematicians convert the data to fit into one view, as you see in the main graphic. A clear relationship emerges between any of the animals, which is explained by the general equation below the graph, with a specific example immediately below it. It is a scale relationship, meaning that just because an elephant, for example, is 37 times heavier than the average man, it doesn't mean the elephant eats, drinks, or parties 37 times more. In fact, that kind of thinking can have tragic results. In 1962, there was an experiment on poor Tusco the elephant. The researchers were trying to see how much LSD an elephant could safely ingest. I'm not really sure how their experiment got approved. Anyway, if a human could safely ingest 1/10 of a milligram of LSD per kilogram of body weight, the researchers thought the elephant could handle 37 times that. Scale says the elephant is 37 times heavier but only eats 10 times as much. So let's start with 10 times more of the drug, not 37 times. Then you may have a temporarily happy elephant, as the left-hand side of our visual shows. If you assume 37 times, that is called linear thinking, and you have the result of the Tusco the elephant experiment, or the right-hand side of the picture. More examples of the power law in action are found in the book, such as a 300-pound weightlifter who is 2 times heavier than a 150-pound weightlifter but cannot lift twice as much. It is less than 2 times. Our second objective in this talk is to apply scale concepts to different areas of interest in higher education. I mentioned Florida and West Virginia in our opening quiz. But let's look at additional examples of how scale and power laws apply to higher education policy, starting with higher education supply, defined as a number and types of institutions in a state. The number of for-profit institutions plotted here on the y-axis grows at a faster rate than state population plotted here on the x-axis. Bigger states have a disproportionately larger number of for-profit institutions. A state that is 10 times bigger than another has more than 10 times the number of for-profit institutions. What might explain this? Maybe for-profit institutions are in high demand in large states, effectively meeting the needs of students. An alternative and less benevolent explanation is that predatory for-profit companies seek vulnerable students in larger states because of the larger populations that present more opportunities for profit making. The reason why scale explains such different phenomena, from biology to higher education, is because there are common characteristics that define these different systems. They are all called complex adaptive systems. A state higher education ecosystem is a complex adaptive system as well, with different actors, such as governments, institutions, and students, all operating within a demographic, economic, technological, and geographic state context. Complex adaptive systems and their predictable patterns are explainable by mathematics or power laws because of what are known as network effects. Essentially, network effects are interactions between and among the different actors that miraculously organize into mathematical patterns. And the more people you have, the more interactions you have. The more interactions you have, the faster, for example, that COVID spreads. All attributable to network effects that organize according to the laws of math. Now, just as we were not able to find a large enough piece of paper to fit all the information for a mouse and a whale, it is also not possible to show a state as large as California, with 40 million people, on the same graph as a state like Wyoming with less than 600,000 people. So again, the data must be converted to fit it all into one tidy picture. This visual shows 6 graphs that look very similar across regular intervals of time, data from the middle of each decade. The small blue dots represent states and the size of their population compared to the public funding they provide to their colleges and universities. There is a relationship between state population and funding for higher education similar to weight and calories for different animals. For all 6 graphs, population increases faster than funding. A state that is 10 times larger than another state invests less than 10 times. One way to think about this is that large states spend less per capita because they gain what economists call economies of scale. A similar pattern emerges for the number of public institutions across the states relative to their populations. In general, a state that is 10 times bigger than another does not need 10 times more public institutions. As a side note, the little equation on the graph has a 0.78 before the x, which tells us this. As an example, California is almost 19 times bigger than New Mexico, but at the maximum needs only 9.8 times more public institutions. Once again, just as we saw that though a cat is 100 times heavier than a mouse, but it only eats 32 times as much, including quite possibly the mouse, we also see scale in action between state populations and public institutions. You may remember that the number of for-profit institutions in a state show a different scale relationship. If we could graph all states on one giant piece of paper, the graph would be exponential, like the spread of a virus. Finally, the science of higher education explores the policymaker question of what do states get for their investment in higher education? To answer this question, we might look at funding across the states compared to their enrollments, or perhaps the number of students they graduate. State funding grows faster than undergraduate enrollments at public universities across the states. A state with 10 times the funding of another state will not have 10 times the number of undergraduates enrolled, which would be desirable, but actually 7.9 times the number of undergraduates enrolled. The information on the graphic addresses the question of what states get for their investment in higher education, a return on investment or ROI question. Each little blue dot on the graphic represents a state. The straight red line best fits all 50 state data points. It has the predicted enrollment and funding for each state. The blue dots represent the actual state funding and actual enrollment for each state. Each state falls a little above or a little below the predicted best fit line. Dots above the red line represent states enrolling more undergraduates than we would expect or predict, given the scale relationship. They would have a positive ROI. Dots below the red line are states that have a negative ROI, since actual enrollment is less than predicted. We can also determine positive or negative ROI for funding versus number of graduates or completions, and those details are in the book. You are probably asking yourself, how does all this apply to policy? When we have an ROI for enrollment and completions, we can construct a 2x2 matrix. Taking one example, let's look at the upper right-hand quadrant. In this situation, a state has a positive enrollment ROI, but a negative completion ROI. The implication is that state policymakers must create or adjust policies to encourage completion, since it is a negative ROI. This next table shows some actual calculations of ROI for a sample of states using real data. If we take California as an example, enrollment ROI is very close to zero. So California public institutions are close to achieving enrollments state policymakers might expect for the funding that they provide. Completion, however, is negative 2.46%. Institutions are not producing the number of graduates that policymakers might expect for the funding they provide. The priority in California should be completion policy. I hope you have enjoyed learning about the science of higher education. We first discussed concepts of scale and power laws as they might apply to cats, mice, cities, and even elephants in drug consumption. The applicability of scale is all around us. Our second objective was to apply concepts of scale to higher education. We looked at funding, state populations, for-profit institutions, public institutions, and even enrollments and completions. Finally, our third objective was to show why this matters, so we discussed return on investment calculations. Thank you for taking the time to explore the science of higher education with me. If you are interested in learning more about this exciting topic, I hope you will go to Amazon and order a copy of the book.